Hello, folks. Welcome to today's lecture, in which we'll be covering a little bit of a history of atomic models. We're going to learn where atomic models came from, and then we're going to look at the best atomic model that we currently so far have, and that is quantum theory of models. And then we're going to learn how we can use what we learn in quantum theory model in order to define the position of electrons around a nucleus or in the atom, and that is electronic configuration. All right, believe it or not, the first atomic model was first initially introduced a very, very long time ago, about 2,400 years ago, by a Greek philosopher called Democritus. Democritus' idea was that if you take an object and if you divide it in half and take one of these portions and then divide that one portion further into another half and continue doing so forever, you will eventually reach a point where you can no longer do that division. You will no longer be able to do that division, and that object simply becomes invisible. It becomes an invisible object to you. And therefore, he called that the invisible object, aka atom. That's where the word atom comes from. He defined that atom to be solid and not necessarily having any internal structure. You're going to have to forgive my handwriting here and this little line that appears very frequently. I don't know, there's something wrong with my stylus. Anyhow, moving forward, then it was a very long time that we did not really tackle this issue until 1803, where a gentleman introduced the modern atomic model. His name was John Dalton, and John Dalton was the first person that introduced the fact that atoms are indestructible, and they cannot be changed, and they are characterized by their weight. They are characterized by their weight, and atoms are what gives rise to a new compound. So atoms get together and they will form a new compound. Aside from that, he didn't really do much experimentation to prove his theory. He was really a physicist that has done a lot of work in gas laws and things like that. But in terms of the atomic model and the instrumentation or experimentation, he hasn't really presented much to begin with. For about 100 years, this was not tackled until we had another gentleman, Joseph John Thomson, aka known as J.J. Thomson. Now, J.J. Thomson had a different perspective. He had a different understanding of the situation, and keep in mind that there's now 100 years passed by. You have 100 years passed by, and you are really looking at a time that chemistry and physics had a lot of different instrumentation and apparatus to experiment what they would believe and improve upon their theories. So what he did is he took an apparatus. This is a hollow tube, and this hollow tube has charges at the tip or the introduction nozzle, and then what he did is injected some gas in here. And when I'm talking about a gas, I'm really talking about an atom, right? Because obviously atoms could be also found in the form of a gas. Now this gas was introduced to this chamber, and as it was passing through this region here, it formed ions. It formed charged particles. It was no longer a neutral thing. Now, once they ionized or they formed charged particles, they were passed through two flats here, these two boxes here. One of them was positively charged and the other one was negatively charged. Now, what was observed by J.J. Thomson was the fact that these ions had a tendency to shift towards the positively charged plate right here, which is the cathode, right? So therefore, the ions had formed this ray, this ray that is highlighted in blue. I'm going to redraw that in red, and this is called a cathode ray. It's called a cathode ray, and he therefore concluded that those particles that were traveling through here must have been negatively charged, because now they are attracted to the positive pole, not to the negative. They're actually going away from the negative plate. They're being attracted to the positive plate, so therefore they must be negatively charged. They must be negatively charged. Whatever they are, they must be negatively charged. So therefore, he coined the phrase electron in 1897, and he decided that they are negatively charged. This is how I write negative. Okay, but he also knew a lot about Maxwell's theory at the time that suggested that particles could actually be deflected once they are subjected to magnetic field. So as a result of that, he came up with the best atomic theory to that day, which suggested that there is a core of positive charge sitting at the core of the atom. And let me change my color here, go to maybe black here. There's a core of this entire thing is positive, and it contains a suspension of negative charges. It contains a suspension of negative charges, and these negative charges were nothing but the electrons. And at the time, he called his theory the plum and pudding theory. That simply was his imagination of an atom. That is, there's an area which kind of resembles a pudding, and you have raisins in them, and these raisins would be the electrons. So they're kind of fluid and kind of, in a suspension of that positively charged area. Obviously, this was not a very complete and a reasonable model, but it was great at the time, don't get me wrong, but it required significant improvement, and it was not for a very long time after. Let me change my color here, and it was, so notice how we have about 100 years here. We have about 100 years to come up with a reasonable atomic model that actually used relatively more sophisticated and complicated instrumentation and a much more elegant approach to define an atom. And then from there, we had about only 6-7 years, well, let's say 8 years, just to be safe, 8 years. I know the math doesn't work, but more or less until it was developed. About 6 to about 8 years that we had another genius that really introduced the first atomic model that was really kind of close to being complete. What Rutherford did was he took advantage of some physical phenomena, and he took a sheet. Let me draw a sheet, a very extremely thin sheet of gold. And then he kind of produced some alpha particles, and in this case, I believe he used radium for that. Radium. This is a radioactive element, and he generated alpha particles. These are just some particles, and these particles have the ability to pass through a lot of things. And what he did is he kind of shoot this thin layer of gold with these alpha particles. Now, based on J.J. Thomson's model, if you shoot this atom, or the atomic model, whatever that is, with the alpha particles, you would expect to shoot, let's say, if you have 100% alpha particles starting on this side, and then you shoot them, and once they pass through that atom, you would typically expect to get 100% of those alpha particles recovered on the left side, so right side and the left side. But surprisingly, that was not the case. And what he saw was the fact that, let me erase these things here. What he saw was that 100% was subjected to that thin gold, but let's say 98%, I'm just making up numbers, but a fraction of those alpha particles bounced back. They actually bounced back, and we know that when something bounces back, that is an indication that it has probably hit a solid obstacle. And after tracing many particles and examining the pattern, Rutherford deduced that the atom must have nearly all its mass and positive charge in a central nucleus, which was about 10,000 times smaller than the atom itself. All of the negative charge was held in the electrons, which must orbit the dense nucleus-like planet around the sun. So the best presentation that he could propose at the time was that you have a positive core that was surrounded by these negative electrons that were orbiting that positive core, much like the sun. So he proposed that this is much like a planetary system. Obviously, there were some flaws and problems with that, and the flaws were addressed by the next scientist. And one of the most important problems was the gravity and the effect of opposing charges, which we're going to see in the next slide. So only about 2 years later, in 1913, in 1913. So again, let me remind you that we have about 100 years here. It's actually very important to appreciate these time periods. And you have about 7-8 years, and then only about 2 years. So you can see that the rate of discovery is insane, going from 100 years to 7 years, and every few years we had a new discovery. So in 1912 or 13, another scientist, Niels Bohr, joined Rutherford, in fact, and he realized that Rutherford's model wasn't quite right. By all the rules of classical physics, it should be very unstable. This model that Rutherford had originally proposed was very unstable. Now, how unstable is that? So let me explain that over here for you. For example, let's say you have a positive core here, and you have this. Let me draw my electrons using a different color. These negative charges that exist in a planetary system like sun and the planet that we have around this core. Now, first things first, you have negative charges that are going around a positive charge. The first question that you'll ask is that, are these negative charges not going to be attracted to that positive charge? And as a result of that, they're gonna just be pulled inside. They're gonna be pulled inside towards the core of that atom. And when that happens, the atom is gonna simply collapse, and we're gonna have a collapse. We're gonna have a collapse of that atom. And a second thing is that over time, while these electrons are orbiting, they're going to lose their energies. And again, they're going to be attracted to the core, and therefore they're going to collapse again. And the last thing is, what if another negative particle passes by? And if it passes by, the inner negative sides, negative signs, these ones here, would be repelled by the crossing by or passing by negative charge from outside. And again, that causes stability issues. In other words, it's going to make the system very unstable, rather. And we would not be able to see the atom as we see, and as a result of that, it would be fair to say that the universe that we observe and experience today will not be in the same form and shape and weight and size. The characteristic and behavior of the universe would be completely different, but that's obviously not the case. So Niels Bohr looked at this, and he immediately recognized that physical sciences in the form of a classical physics cannot possibly explain the best atomic model. And luckily, he was very familiar with Planck's quantum theory, and he was able to combine all physical sciences that we knew to that date in order to postulate and come up with a new theory. So what he was able to measure was the fact that there is a ratio of the energy and the ratio of the electrons, the ratio of the energy of the electrons, and the frequency of their orbits, around the nucleus were both equal to a number that is called the Planck's number, or Planck's constant, and it's a very weird number. Now, what is this number? We don't care. We're not here to learn what Planck's number is or Planck's constant is, but just take it that it's very complex, and it is a number that is derived from the ratio of energy of electrons versus their frequency of their orbits. and they happen to be the same. Now, what does that really mean? Let me just change my color here and let me explain what that really means. That simply means that the area or a container or wherever electrons exist, if you think about them as being a container, now electrons, let's say I have one electron that exists here. The electron is only going to exist in that container. Let me call this container A, container B, container C. So if the electron wants to go from container A to B, once it leaves container A, it has to go into non-existent state of matter and then re-existence of a matter in container B. So in other words, the energy level of container A is a set value. It is a set value. It's not going to change. It is not continuous. It is a set value. It has restrictions in its quantifications. So therefore, they called it a quanta. It's called a quanta. Quanta is simply referring to a defined amount of energy. It's a confined amount of energy. So if an electron from container A would like to go to container B, it has to get out of the existence and then reappear in container B. That's a very, very complex and unfamiliar concept that we're dealing with. So in other words, electrons jump. They jump between energy levels. Now these containers are the energy levels. So in other words, an electron cannot exist outside these containers. They cannot exist outside these energy containers, and they have to exist in these energy containers. We call them quantas, and these quantas have a set value for their energy level. All right, okay, so now I'm going to go ahead and list five criteria that are found in Bohr's atomic model theory. Now, the very first one suggests that electrons orbit the nucleus in orbits that have a set size and energy. I just talked about it in a greater detail, but I'm going to demonstrate it using a little bit more scientific depiction here. So, if you think of this whole race of circles here to be the atom, obviously the core is going to contain the positively charged particles, being proton. It also contains neutron, which is obviously neutral. It does not carry any charges, so therefore you can perceive the nucleus to be positively charged and getting that charge from a proton. So each one of these layers, each one of these circles, I'm not sure if you guys can see where my mouse is moving, but each one of these guys will have a set amount of energy and size. So N1 will have a unique size and energy, which is different than N equals 2, which is going to be different than N equals 3. And electrons will only exist within those energy levels. So in other words, an electron cannot exist in between. Electron cannot exist in between. Let me write this down. Electrons cannot exist in here. They cannot be in here. They have to be on the dotted lines, and each one of those lines, one of those circles, will represent a particular kind of size and energy. Now, the next one is that the energy levels that are closer to the core, to the positive sign, to the nucleus, are going to be lower. They're going to be lower in amount of energy. So in other words, the amount of energy is going to be increasing inside out. It is going to increase inside out. So as a result of that, you can conclude that N1 is going to be lower in energy than N2, which is lower in energy than N3. Now, just to better understand this system, you can think of these energy levels as being rooms within a house, within a building. So electrons will exist in those rooms, and those rooms will have different energy levels. All right, now moving away, obviously the electrons that exist in, let's say, N1 are also going to have lower amount of energy than electrons that exist in N number 2 and N number 3. So the closer you are to the core, the closer you are to here, the lower the amount of energy for both the orbital and the electron will be experienced. All right, now electrons will fill up the orbitals, and they will fill from the lower amount of energy to higher. So again, it's going to be inside out. We're gonna fill up inside out within the same direction. We're gonna fill up within the same direction, moving away from the core. And each one of those orbitals will have a very restricted number of electrons that they can accept. Once that number is reached to the capacity, only then a new energy level is created. What does that mean? That means that if you have placed, let's say, 2 electrons here, and N number 1 can only take 2 electrons, that means that it cannot take 3, and that is the maximum number. Only then the second orbital, which is N2, N2 is going to appear, or it's going to be made available for the remaining number of electrons. So in other words, you cannot first go fill N number 2 and then come back down to fill up N number 1. N number 1 is going to be filled first, then number 2, then number 3, then number 4, and the show goes on. And the last thing is radiation happens when an electron moves from one level to another. So for example, if you have an electron which is pre-drawn here in green, let me go to green so I'm consistent with it. I'm talking about these two here. If electron that exists in N number 2, energy level number 2, would like to go down, therefore it is going from a higher energy level to a lower energy level. So you're going from a very large energy level to a very lower amount of energy level. There is a size difference between the energy levels here. That size difference is going to be an emission of light. An emission of light. So when an electron is going from a higher energy level to a lower energy level, obviously there is some leftover energy. There's some outstanding balance of energy, and that energy is really emitted in the form of light. All right, okay, so now let's have a look at one example to see how we can actually fill up these orbitals in the Bohr's model, atomic model. So let's say we're working with sodium. Now for sodium, which is a metal, it is a metal sodium, it has 11 protons. It has 11 protons. Obviously, it will also have 11 neutrons, but it also has, oops, let me erase this. It will also have 11 electrons, 11 electrons. So it should not be a surprise to you that all the positive charge is found in the core right here. So you will find all the 11 protons in a core. That's a very dense positive core. That's a very dense positive core. All right, now let's see if we can position the electrons around here. Now N number 1 only accepts 2 electrons. That's how it rolls. That's the rule. That's the law. N number 1 only accepts 2 electrons. So I got one here already and a second one. So obviously I have another 9 to fill up. Now N number 2 also accepts 8 electrons. That's the rule. It accepts some electrons, but it's a total of 8. So I got 1, 2, 3, 4, 5, 6, 8. I'm sorry, 7 and 8. So that means that I have now filled up a total of 10 electrons of those 11 electrons. I'm only left with 1. Only then I'm going to go ahead and place the last one on the last shell, which is N number 3. So this example is demonstrated just to show you that you cannot go ahead and fill up n number 3 first and then go to n number 2 and then n number 1. You have to go in this direction. N number 1 is filled first, then number 2, then number 3. Now, Bohr's theory that electrons exist in set orbitals or orbits around the nucleus was a key to the periodic repetition of properties for the elements. However, at the time, many people were very skeptical about this discovery or introduction of theory, and people still had not accepted the idea of quantas or set containers of energy, essentially, or they simply found flaws in this theory, because Bohr had used a very basic atom as a representative or a subject to study. But there was pretty good evidence to suggest that this theory was a very good theory up until that day. However, there was one problem, and the problem was that it could not address the concern of electrons traveling trajectory, or it could, in other words, it could not explain how electrons would travel. And we know that electrons do not travel on a specific orbit or a pathway, and that was a gap in the theory, and that left the gap open for the future scientists to come in and fill it up and complete the task. And that was no one else but to be discovered by another genius of the time, Erwin Schrödinger. Okay, so then in 1926, we had another genius that came up with the most complete atomic model that we know so far, Mr. Erwin Schrödinger. He said, wait a minute, I really admire the work of Niels Bohr, but there are some flaws in it, and I'm going to have to correct that. So he took advantage of what he knew at the time, and that was the Heisenberg's uncertainty principle. And Heisenberg's uncertainty principle states that you cannot know the location. You can't know the location. So the position, in other words, you can't know the position of an electron at the same time when you have information about its momentum. So you either know this or you know this. You cannot know both of them at the same time. So in other words, there's only the probability of predicting the location of the electron. So looking back at what Niels Bohr predicted, that there are energy levels that would contain of those electrons, and the electrons are definitely within those orbitals, Schrödinger said, hey, wait a second, we can't definitely say where within that orbital the electron is going to exist. So we don't know what the position of that electron is, but we can only predict using mathematical models where the probability of that location is. However, the atomic model that was suggested and introduced by Erwin Schrödinger was built on the existing atomic model that was suggested and introduced by Niels Bohr. So, in other words, Erwin Schrödinger took everything from Niels Bohr and made it slightly more, well, not slightly, way more better, way more complicated, accurate, sophisticated, and a lot more mathematically complex. So let's have a look to see what this gentleman has done for us. Okay, so this is the atomic model that was presented by Niels Bohr. This is Niels Bohr. Okay, Niels Bohr said, I have different energy levels. I have energy level 1, I have energy level 2, and 3. And within these quantas, and these containers, if you will find electrons. Then Schrödinger came along and said, wait a second, I agree with the majority of your claims and the way that you look at the atomic model, but I'm going to have to tear the whole thing down and rebuild it using your same principles and concepts, but I'm going to make it better. I'm going to introduce a different way of describing your energy levels, and I'm going to rebuild these shells that you have created. So he reconstructed that building. So this is more or less the same, but this is a reconstruction. What you see on the left is on the right, that is proposed by Erwin Schrödinger is a reconstruction of what was previously known and proposed by Bohr's model. So he said, Erwin Schrödinger said, you know what, I'm going to change that structure within a building. First of all, we're going to have floors. So we have a massive building that is going to contain all of our electrons. And within that building, we're going to have different floors. I'm going to have the first floor, I'm going to have the second floor, I'm going to have the third, fourth, fifth, 6, 7, and so on and so forth. So these are different levels. These are different floors. These are different floors to the building, and each floor has its energy level. So there's a little bit of a difference here that within each floor, you still have different rooms. So for example, on a first floor, you only have one room, and that room is called S. That's the S room. That is the S room. And on the second floor, you have, well, essentially two different kinds of room, but a total of 4 rooms. So you have one room that is S room, and you have 3 P rooms. Each one of these rooms are going to be one orbital. Now, the concept of orbital is going to change here. Now, these are the new orbitals. So, just to recap, we now have introduced a new way or a new definition of orbitals, and these orbitals could be perceived as different rooms within a floor that is found in a big building that is called your atom. Okay, now, there's one more catch here, and that is that each one of these, let me change my color here, each one of these, go to green, each one of these rooms can only receive 2 electrons, and we're going to show these 2 electrons using 2 half arrows. One goes up, the other one comes down. So therefore, the first room is going to receive 2 electrons. That is the S orbital, and it's called 1s because it is suggesting that it is on the main floor, if you will. It's on the first floor, and you're going to go to S room, and in that room, you're going to find 2 electrons. Now, that is the capacity. There are no further rooms on that floor. So you're going to have to move up to the next floor. The second floor, you again going to go into the S room, and you probably will find 2 more electrons. And then within the same floor, you're going to have other kinds of rooms that are labeled as P. And each one of them is going to receive one electron. And so on and so forth. Just like that. All right, okay. So moving forward, now we're going to get into the electronic configuration. So what I have simply drawn in this big box here is known as electronic configuration. Electronic configuration of an atom. Electronic configuration of an atom. All right, so moving forward, I'm going to demonstrate a couple of examples, and we're going to go back to the periodic table, and we're going to pull some atoms out, and we're going to do their electronic configurations. In other words, we're going to build a house for them, a building for them, and then we're going to start filling their rooms with their corresponding electrons. Okay, let's get started by the first example. All right, let's have a look at the first example, fluorine. Okay, as the periodic table suggests, we have a total of 9 electrons that will require room within this building that we call the atom, the fluorine atom. So we're going to construct a building, and we're going to construct a building for fluorine. All right, let's go ahead and position all these 9 electrons within their rooms. So obviously, we're going to have to get started by the lowest orbital. Why? Because that's the lowest in amount of energy. So notice that this axis over here is showing the energy level, and as obviously we are going up one floor, the energy level is going to increase. So would the energy of the electrons within those floors. Okay, let me change my color here. Okay, I told you earlier that we're going to show the electrons with half arrows, just like that. And one goes up, and the other one's going to come back down. We're not going to do both up. That is not okay. This is okay. This is not. This is not okay. This is not okay. Okay. All right. So first floor, on the 1s, we're going to have 2 electrons. And we do not have any more rooms on the first floor. That's the only room on the first floor. And that has already maxed out its capacity because we have a limitation of 2 electrons per a room. So we're going to have to go up 1 floor and find the first or the lowest energy room, and that is 2s. We're going to place 1 and 2 electrons in that room. Then on the same floor, we're going to have to find 5 more spots for the remaining 5 electrons in the 2p orbitals. That is suggesting that that is on the second floor, but this time instead of the s room, they're going to be called the p room, and they're very, 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 very marginally higher in amount of energy as opposed to 2s. Okay, so the way we're going to fill up the 2p orbital is we're going to place 1 electron in each room first. So 1, 2, and 3. Then we're going to come back. And put the remaining electrons in the rooms. So what I have not done, let me show you here. What I have not done is to go like that. I understand that the outcome is going to be the same, but the order at which you write it is very important. You do not want to make a mistake on that one. It becomes a little bit more obvious in the future examples. So what we're going to do is, this is not okay. They appear to be the same, but the order at which I filled up the orbital is not the same. So go in each orbital first. So 1, 2, 3, and then come back to fill up the remaining in those orbitals. Now, obviously in a test or in science or whenever we're talking about electronic configurations, we will not have the flexibility and the luxury of having a lot of time and space to draw this humongous table. So we're going to have to come up with a creative way to simply shorten this and write it in handwriting. So the way I'm going to show what the electronic configuration of fluorine is, after I have placed it in the building, I'm going to come back here on a left side, and I'm going to write down in order those orbitals that contain currently the electrons in them. So therefore, it's going to be 1s, and on that 1s, I have 2 electrons. This is not to the s to the power of 2. It's just suggesting that on the first floor, in the s orbital, I have 2 electrons. Then on the second floor, I have 2 electrons in the s orbital, aka the room. And on the same floor, I have 5 electrons in the p orbital. So the electronic configuration of fluorine becomes 1s2, 2s2, 2p5. I'm going to read it back to you guys. It's going to be 1s2, 2s2, 2p5. So it's very important that you'd be able to read it that way and also write it that way. So a couple of notes. Please don't write 1, 2s. That's not good. Don't write 1, 2s. Things like that. And don't do 1s2. None of these things over here, none of these guys are good. They're all wrong. The only correct version of presentation of electronic configuration is this one right here. Okay, now let's move to the second example. All right, what do we have here? We have neon. So it's literally 1 extra electron here. Okay, starting from the lowest energy floor. Therefore, that's going to be 1s. And we have a total of 10 electrons. So I got 1s that contains 2 electrons. Then I'm going to go to the next floor. I do not have any more rooms on the first floor. I got to go up to find the first unoccupied floor, so the 2s orbital. Then I have I got 6 more electrons to fill up in the 2p orbital. the way I'm going to write it is 1, 2, 3. Then what I'm going to do, just to show the importance of going in that order, I'm going to then fill up the electrons with a different color. All right, so if I want to rewrite the electronic configuration of neon in this case, this will be 1s orbital that contains 2 electrons here. Then I have 2s with 2 electrons there, and then I have the 2p orbital that has 6 electrons. Now, just to recap and a flashback to the previous models that we had. Remember, we talked about the octet rule, and the octet rule suggested that the last orbital should always contain 8 electrons. Now, you can think of the last floor being a second floor that contains a total of 2 and 6, 8 electrons. That is why neon is a noble gas, and it does not really want to react with any other elements. Now, I have presented neon here because of a very, very important utility that neon or all the other noble gases in this last row will have. Now, that will become more evident once I present the next example, and that is chlorine. Okay, now chlorine's got 17 electrons, so I got a total of 17 electrons in chlorine atom. All right, let's go ahead and fill up the rooms for chlorine. Obviously, we're going to get started by the lowest energy level. I'm repeating myself multiple times to make sure that you guys understand the importance of these things. All right, so first floor is going to receive 2. Second floor is going to receive 2. Third floor is going to receive, second floor, different room is going to receive 6 electrons. So far I've got a total of 10 electrons that will leave me with an outstanding balance of 7 electrons here. Okay, so I've got the 3s orbital here. Now for the 3p, I have 1, 2, 3, and then I'm going to come back here and I'm going to fill up again 1 and 2. So always recount the number of electrons to make sure that you're not making a mistake. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So I got a total of 17 electrons, and that is consistent with what I had in chlorine. So let's go ahead and write the electronic configuration for chlorine. I have 1s that I have 2 electrons in. Then I got 2s. Again, I got 2 electrons in. Then I have the 3. Then I have the 2p with 6 electrons. Then I have 3s2 and 3p5. That would be the electronic configuration of chlorine. Now, just pause for a second and imagine what if you had an element that had a lot more electrons than any of the examples that I had presented to you. We got a lot of elements in the periodic table. They have a lot of electrons in their shells. So, they have 80s, 90s, 100s. But we don't really have time to sit down and write all those individual orbitals as I have done here. So, in order to save time, what we can do is that we can take advantage of the last complete noble gas in the periodic table before that element of interest. So for example, we know that the last element that has a full electronic configuration is neon. So what we can do is to save time and consider all this to be neon, because neon's got 10 electrons, so I got 2, 2, 6, 4. So up until here is really the electronic configuration of neon, and then just write neon and then followed by the remaining electron configuration. All right, that's the fastest way to present large elements that have a lot of electrons in their atomic buildings. Okay, now before I take you guys through the next example, there's something very interesting in this chart here that some of you guys may have noticed already, but I'm gonna explain it here to you anyways. So look at the energy level. Look at this axis here. Look at the energy level. And from what I had told you so far is that obviously energy level first floor is lower than the second is lower than third is lower than fourth is lower than fifth, so on and so forth. However, if you guys look in here, you will see that, for example, on the third floor, when you have the 3p orbitals or rooms, then you're going to go to 4s, but then before you go to 4p, you're going to go to 3d. Now, what is d? First of all, D is just another room. D is just another room. Very much like another room. Very much like P and S. So we have, well, let me put them in the order. Let me place them in the order. So you have the S orbital, you have the P orbital, then you have the D orbital, then you have the F orbital. So these are simply different rooms within different floors, but their energy levels are not necessarily always continuous and consistent with one another. As you've seen that before you go to 3D, I'm sorry here, you're gonna have to go to 4S. And it is very strange that these rooms happen to be slightly higher in energy than 4S. Now, this is what we know. This is what we know as off. Actually, let me erase this. This is what we know as Aufbau's principle. Aufbau was a German chemist that suggested that the order of subshell electron orbitals are going to be in this order. So this is pretty clear in this little diagram that I have on a far right side here for you guys. So when we're filling up the electrons in their orbitals, we're going to go to 1s, 2s, then we're going to go. So we're going to go in this direction. We're going to go to 2s, then we're going to go to 2p, 3s, and then we're going to go to 3p. But before we go to 3d, we're going to have to fill up 3s, and then we're going to go to 3d, and then we're going to go to 4p. But before we fill up 4d, we're going to have to go to 5s, so on and so forth. And this is something that you have to memorize. This is something that you have to memorize. This is something that you have to know. You got to know this. You got to know Aufbau's principle and order. So let's have a look at one example. And that example is bromine. So you have a lot of electrons here. You have a total of 35 electrons. So let's quickly go ahead. You guys should be the master of this right now. Let's go ahead and quickly fill up all the electrons here. So I'm going to go to 3s, then I'm going to go to 3p. Notice how I'm not skipping, and I'm doing this in a proper order that is required of us to do. All right, I got these, but after 4s, I'm not going to go to 4p. I'm going to go to 3d. And d orbitals will receive 10 electrons. So s receives 2, p we got 6, and then d we got 10 electrons. And then I'm gonna go to 4p, and in that 4p I got 1, 2, 3, 4, and 5. Now, when you do the electronic counts, the total that I have here will add up to 35 electrons. All right, now let's go ahead and write down. Let's go ahead and write down the electronic configuration for bromine. But obviously, we're not going to sit down and write all these things. We could, but I mean, just to save time, as I have shown you, we're going to go to last filled noble gas in that periodic table. So we're just going to say, we're going to get started, instead of 0, we're going to get started from argon. And from argon, we have 3D10, then we have 4S2, then we have 4P5. We have 4P5. Now let me change my color here because I want to show you that all of this is the electronic configuration of argon. Is the electronic configuration of argon. All right, so we have covered the history of atomic models, and we kind of learned what Mr. Erwin Schrödinger suggested to be the best atomic model, which was relying on quantum physics. And then we dived into the concept of electronic configuration, and we've learned how to write electronic configurations. And with that being said, it concludes our Module 3 electronic configurations lecture.